Are you being able to see the screen?
Yes, sir.
Hello? Yes. Okay. So we have been looking at this M of n system, and any questions on this M of n system? M of n system is a system where M out of n components must be working correctly for the system to work correctly. And we said that the reliability of an M of n system is as the equation provided here. Any questions? Everybody could understand this equation? Any questions on this equation? Yes? Fine, right? Hello.
Yes, sir.
Yes, sir.
Okay. So then today we will start with unit level modular redundancy. So we saw this n modular redundancy and triple modular redundancy in particular out of n modular redundancy, which is applied at the system level. So each component is essentially the entire system. And then today we will be looking at a structure, a redundant structure, in which the redundancy is not applied at the entire system level, but within individual subcomponents. For example, let us say that you have a system like this here, and essentially in this system, it is how is the system? The system is basically like this. You have unit 1, it connects to 2 units, unit 2 and unit 3, and the output of both of them goes to unit 4, which produces the output. So this is the system. The original system is this. Very badly drawn, I understand, but the original system is this. Now we were taking this entire system as one box in the previous discussion. Now we are saying that instead of applying, and we saw that in such a system, the correctness of the voter becomes very essential. If the voter is unreliable, then the entire system can be can the reliability of the entire system can become very low. We were trying to find determine techniques where the dependence on the voter could be reduced. So unit level redundancy is such a system. So you see that we at the left side we have 3 copies of unit 1. So the 3 copies of unit 1 all take the same input from the environment. These are the inputs, all take the same inputs, and their outputs are fed to all the voters, and you have 3 voters. So all the 3 voters receive inputs from the 3 unit 1 outputs, right? Now the outputs from the outputs from each of the 3 voters, suppose say this voter 1 goes to unit 2 here, this voter goes to the second unit 2, and this voter goes to the third unit 2. Similarly for the other side as well, voter to unit 3. hmm. So now what happens, you see that if one unit is, suppose there is a problem with unit 1, one of the unit 1s, the voter will be able to mask that because 2 units will be correctly working. Now if let us say a voter at this level, Suppose this voter is not working correctly. This voter is not working correctly. So then what will happen? The input to unit 2, this unit 2, the input to this unit 2 will be wrong, right? The input to this unit 2 will be wrong, and the input to this unit 3 will also be wrong, right? Now, however, because this voter and this voter, the two other unit 1 output voters, they are working correctly. So the input to the second unit 2 and the third unit 2 and the second unit 3 and the third unit 3 will be correct. Now, so therefore there is a mistake to one unit 3, but the other two unit 3s are working. Now because this output is working, then what happens? Then the output, this output is wrong, this output is wrong. However, this output is correct, this output is correct, all other this output is again wrong, this output is wrong, but two of the outputs are correct. So all these three voters will essentially give correct outputs. Okay. And there is one more property. So again, so all these three voters will give you correct outputs. Now, so therefore, there was one problem that was solved. That, see, although a voter was not working correctly, we could mask that error, and that error just propagated to one level, meaning that the entire system, I mean, at this layer, if you see at this layer, the system is again fully correct. All outputs are correct. So the error could be corrected just within one level. Hmm? So the error propagated only to the next level of units, but the subsequent units will not see the error anymore. That is the beauty of this approach. And there is another very important. So two things are achieved. One is that the dependence on the voter is no more than the dependence on a single unit. So failure of a unit and the failure of a voter is same. The second important thing is that the error in a voter or at any unit error on any error propagates to at most up to the next level, and then it can be solved. However, the aim out of n criteria still needs to be fulfilled. That I need to have a majority quorum, that majority of the output should be correct. That has to be there. But two important things, as I told you. One is that the dependence on the voter is same as the dependence on the unit. The voters are not unduly there is no undue importance given on the voter. The second is that propagation of the error only goes up to the next level. Okay. The level at which the replication and voting are applied can be further lowered at the expense of additional voters, increasing size and delay in the system. So what is this point saying? This point is saying that yes, fine, now we saw that if we could increase reliability by what? I can, instead of taking unit 1, unit 2, unit 3, I can just go deeper and just find out the subcomponents within unit 1, subcomponents within unit 2, subcomponents within unit 3 or unit 4, and then apply this NMR, this same strategy at a deeper level. So although the reliability will increase, two important things will increase. One is size, rather also cost, and the delay in the system. You see that whenever you are doing this, you are adding one level of voters, and if the system is working with a clock, although the reliability increases, the delay in the system is bound to increase. Any questions? Yes, is this okay? Hello, are you all doing
Yes,
the
sir. Yes,
class?
sir.
See, I need your inputs because I am not being able to see anybody. This is not a physical class. So I need your inputs. Okay. So there is one particular system of importance of which is worth mentioning is this replicated processor memory system. In this system, you have, so in any von Neumann architecture, you have a memory connected to any computer system. Let us say you have a processor connected to memories, and processors talk to memories for all its data, instruction, etc. They need to talk to memory. Now, therefore, memory is critical. So fault there has to be somehow captured and controlled. So there we are using here, for suppose you have a spacecraft and or a nuclear reactor, and things need to be extremely safety critical. They are safety critical and it cannot fail. So one system where safety can be improved by which is this replicated processor memory system. Here all these links are bidirectional. These links that you sorry, all these links are bidirectional. These links are bidirectional links. So a processor, suppose, talks to memory and the memory provides the output. All these three do the same thing. They ask for the same thing. If they are actually running the same code in lockstep, and they are producing the same output, and their outputs are being voted, and it is going to the memory for instructions, and it is going to all three memories. So suppose you are asking from the memory, accessing the memory for some data. So all three processors are executing in lockstep. If they want some data, so they actually produce this what they want. They talk to memory, and then the same output comes. Or say you want to store some data in memory. Let us say you want to store some data in memory. So what are you storing? You're storing the output of the processor into memory, and the processors are running some code, and they are running the same code in lockstep. So all of them are producing outputs. So if two of the processors are working correctly, then these voters this voter will produce a majority, will vote on the output of the processor and produce some output, and this output will be put into the memory. Okay, all the three memories. Why all the three memories? Because these links are again bidirectional, as I said. So the output is coming to this memory, the output is going to this memory, and the output is also going to this memory. Similarly, from all the other voters as well. Okay, from all the other voters, this output is going. And on the other side, what is happening? The memory, suppose now the processor wants some data from memory. From the memory, your output comes this side. So from all the memories, the output goes to all the voters. From the memory, the data is fetched from all three memories. It goes to all the voters. It is voted, and the voted output goes to the back to the processor. So again, you are getting a voted output, right? So if only at least two of the processors are working correctly, at least two of the processors are working correctly, all the three voters, the majority of all the three voters will give you the correct result, right? So then the memory will check, and the memory will put the majority out of the three voters and put it in the memory, and the data from the memory again on the other side will likewise go from it to all the processors. Any questions here? Any questions? Otherwise, I will go to the next. This is done here. if there are no questions.
No, sir,
Yes.
no question.
No. Okay. Then we come to something called dynamic redundancy. Now, previous variations of NMR need considerable hardware to instantaneously mask error. So now what happened when we are having NMR, we saw that we require, one thing is that we require a lot of hardware, be it communication hardware or say processing hardware, whatever it is. We require a lot of hardware. The other way is that we do not run all of them together. We dynamically add spares when the primary module is not working correctly. So temporary erroneous results. So for which case is that okay? Temporary erroneous results may be acceptable if system can detect such errors and reconfigure itself by replacing the faulty module by a fault-free spare. So I have an active module. So I have an active module. This is the active module which is currently working, and I have this n spares. Now, if the active module is working, and then the output of the active module goes to this fault detection and reconfiguration unit. So what does this fault detection and reconfiguration unit do? It detects faults in the active, if any, and if it detects the fault correctly, then it will and if the active is when the active is faulty, then it will replace the active with one of the spares. So the first easy thing is that if all are active together, not they are not spares, if all are active together, then what will be the reliability of the system if everybody has the same failure rate? Then this is it. This is what it is. This is what it is. What is it saying? It is saying that the reliability is given by RDRU. So what is RDRU? Reliability of the detection and reconfiguration unit multiplied by 1 minus 1 minus RT to the power n. So what is 1 minus RT to the power n? We are just thinking that all these spares, all these pairs are essentially running in parallel. So if any of the spares are working correctly, then you what you are saying, then your system will be okay. And what is RDRU? RDRU is saying that it is the probability that the fault in the active will be correctly detected. If the fault in the active is correctly detected, then given n spares, if it just forms n in parallel components. So these n spares are n parallel components. Any one of them works correctly, the system works correctly. The only catch is that what about this fault detection and reconfiguration unit? So when the active is running, fine, the active is running. Now what is the probability that a fault in the active will be correctly will be correctly diagnosed? That is RDRU. RDRU. So this is not the total. I will just, this was missing. This is nothing. Just a minute. See, what am I trying to do? What is this part? What is this part? Can I go into this interactive mode? Can the students tell me what is this part telling?
Sir, 1 minus RT raised to n is all these pairs failing together.
Yes.
All the n
And
pairs failing
RDRU?
together. And
Yes.
RDRU is the reliability of that fault detection and reconfiguration unit.
Right. So what does RDRU into 1 minus of 1 minus RT to the power n trying to tell me?
That is the reliability of, if you combine that fault detection and the spares, reliability of that bunch,
Yes, yes,
cluster
yes,
then.
understood. But understood what you're trying to say. Can you tell a bit more clearly? Is it possible? Otherwise, I will say.
Sir,
Some,
like
when will RDRU come into the picture? Rather, why have I added this R act? Saying that R act is the reliability of the active module.
So when R act fails, then RDRU comes into picture.
Correct. So R act will anyway be there. That is the reliability of the active module. When the active module fails, then we are saying that RDRU, the probability that RDRU will be able to correctly detect the failure of the active module and and will be able to reconfigure is RDRU. So RDRU is the probability that in the case in which the active module fails, what is the probability that the this fault will be detected and correctly reconfigured. Now when, so given this reliability, what is the probability that the system will still work correctly in the presence of the active module failing? That is 1 minus or 1 minus RT to the power n. So the entire reliability will therefore be this. Is that okay? Any questions?
So that active module is sufficient alone, or should it be multiplied by RDRU2, that R act?
See, what is R act saying? R act is the reliability of this one. So R act tells me the probability that the active module will work correctly. This probability will always be there in the system reliability. Now, in the case in which R act fails, in the case in which R act fails, the probability that that failure will be detected, that is RDRU. You want to say that here also you want to multiply with R act? Here also you want a multiplication with R act? This is what you are saying?
No, sir, I'm saying with R act, if you multiply RDRU, RDRU is reliability of
Why
that.
should that be? See, why have I put in this R act? This R act is here because we are trying to say that the probability that the active module will be work, because the system is getting output. The output that is coming here at the output is only due to R active. Somebody is there as R active, right?
Okay,
So
okay, yes, sir.
in any case, R act, the probability that you are you are getting correct output from the active is R act. Now in case when the R act fails, the probability that it will be detected is RDRU and reconfigured is RDRU, and in that case any one of the modules will be able to take charge, any one of the spares will be able to take charge. That probability is 1 minus of 1 minus RT to the power n, right?
Right, sir, right, okay.
Okay. Now so let us see that what is the reliability. Here is a question, small question again. What is the reliability of a system with a single active and a single spare module, given C is the probability that the faulty module will be correctly diagnosed and disconnected and the good spare will be successfully connected? What will that be? This is it, right? See and tell me yes. The same thing with two modules. Right?
Sir, here the active module also has that reliability R of t, right?
What is the reliability of a system with a single active and a single spare module, given that C is the probability that the faulty active module will be correctly diagnosed, that the faulty active module will be correctly diagnosed and disconnected, and the good spare will be successfully connected. Okay. Oh, okay. So what I missed in the previous one here, sorry, just a minute. What I missed here in the previous one is that I should have added this. Is this okay? This is what I missed. I was thinking, but I missed it. Now is this okay? The
Yes,
previous
sir.
one,
So,
right?
so now you are like the 1 minus R act is for like detecting whether the active is fault,
No,
right?
so
Including.
it is just like the cases that we studied in our parallel and series. Remember, we were
Yes, sir. Yes.
arguing about a series. So one is that when R act is working, the other case is when R act is failing. So in case R act fails, so 1 minus R act is the probability that that the active is not working correctly, into the probability that it will be detected, that is RDRU, into the probability that any one of the n modules will come into the picture and be able to handle it. Right? Is that fine? Then we can proceed if this is okay.
Yes, sir.
Yes.
It's fine. Yes.
Okay. So now let us look at it in a slightly different way. Let us say that you have this system, and your failure rate, you have lambda. Failure rate is constant and is lambda. Now in that case, we know that when the failure rate is known, then when the failure rate is known, then your reliability is given by e to the power minus lambda t, right? E to the power minus lambda t is the reliability. Now in case, means I am just trying to say how you can look at it in a different way as well. When lambda is known to be a constant with the constant failure rate of the modules. So e to the power minus lambda t is the reliability of the system. Now if C is the probability that a faulty active module will be correctly diagnosed and a good spare will be successfully connected, then 1 minus C is the probability that the spare will not be diagnosed, that the fault will not be diagnosed correctly. So if the fault is not diagnosed correctly, then for such a case, 1 minus C into lambda is the rate at which faults will occur in such a system. Lambda was my original rate of failures. Rate of failures of the active module. Now I am saying rate of failure of the active module is lambda. Then I am saying that C is the probability that a faulty active module will be correctly diagnosed and disconnected and a goods pair will be successfully connected. So if this is C, is this probability, then 1 minus C is the probability that the faulty active module will not be correctly diagnosed. Right? And let us say, I'm just saying the other cases. If this happens, then what will happen? Then in that case, what will be the reliability of the system? e to the power minus 1 minus c lambda t. What is this? This is the probability that, 1 minus c lambda t. This is the probability that the reliability for the case when, this is the reliability for the case when you have an active module with a constant fault rate lambda, and with C being the probability that fault in this active will be correctly diagnosed and disconnected and successfully replaced. With this, if I multiply RDRU, why RDRU is still required? RDRU, because in this case, in this example, we did not talk about RDRU. So if we have RDRU, probability that the active module will be correctly diagnosed I have maybe just a minute. I will verify and tell you in the next class, but I think we require a RDRU here as well. And I'm trying to tell you why I think this. Why I think this. At least according to the logic that I'll try to explain to you, you need an RDRU in this as well. Why? Because C is fine. C is the probability that the faulty active module will be correctly diagnosed, disconnected, and the goods pair will be successfully connected. On what does this depend? It depends on the output that is produced by the active module. So how does a fault detection and reconfiguration unit detect a fault? Based on the outputs that will be provided by the active module. Now, this active module, the outputs could be in such a range that you could not detect the fault. The output, based on the range of outputs or something, the fault detection unit will run some test based on what output the active module is producing. Based on that, it will try to detect an error in the active, right? So the probability that an active module, a fault in the active module will be correctly diagnosed, this C, is based on the assumption that the fault detection and reconfiguration unit is correctly working. The reliability of the fault detection and reconfiguration unit itself is not included in C. C is the probability that given a correctly working fault detection and reconfiguration unit, what is the probability that the fault in the active will be correctly diagnosed, disconnected, and a good spare successfully connected? Have I been able to make my point? Are you with
Yes,
me in
sir.
this?
So like
Yes.
C doesn't include that detection part, so we need to
Reliability
include
of
sir.
the fault detection and reconfiguration unit.
So
Why? Because the it is not that suppose the fault detection and reconfiguration unit is perfectly fine. Will it be able to discover all faults in the active? May not be so. Why? Because the faults may be in such a the output of the active may be in such a range that it fails to detect that fault in the active. It could be. So C is actually taking into consideration that probability. And if this is the case, then RT has to be there. C, then RT plus C into RT into 1 minus RT has to be there. But it has to also include the multiply. It should also have this multiplication with RDRU, because RDRU is actually the reliability of this detection and reconfiguration unit. Hello, am I okay?
yes, sir.
Yes.
Uh,
Only not from Vinay. I'm getting this voice is that of Vinay, but how many people are doing this class? By the way, I did not. Okay, by the today's at the end of today's class, I'll try to understand what is the population like in this class. I have not taken that as well. How many BTechs, how many MTechs? I do not know. But somebody else as well from the BTechs who are doing this class. Have I been able to make my point?
Yes, sir, it's clear.
Yes, correct. Correct. So,
sir,
yes.
in the probability, will there be something like so a reliable system? So if the detection system like falsely detects it as a 40 and then try to change it, will there be some cases like that happening?
Hello.
Sir, like a misdiagnosis, like the RDR is the detection system, right? So can it like falsely detect? Suppose the system is working and then it is like uh,
Ah, that part. No, no, no. That part we have not covered here. Understood what you're saying. You're saying that what happens if the active is correct, working correctly, and it detects that it is wrong.
yes,
If that is
yes, sir.
so, yes, that part we have not seen. But in any case, even if it detects wrong, you have the spares to take care of it. That part we have not. That part we have not seen. Understood what you are saying.
Okay, sir.
But then the for the case in which I was saying that what happens when let us say that I will always have a spare to put in. That part I am saying that I guaranteed that I'll be able to put I'll always be able to put in a spare. In that case, if I have a constant failure rate lambda, and if I have C, then what will be the system reliability? It will be given by something like this: R equals to R DRU into e to the power minus 1 minus C lambda T, with the assumption that I'm always being able to get a spare to put in. I just did not include this part. RT, this spare part we have already seen what will happen. This thing I have not included. Understood, na? If I want, if I just have these spares, I have to just multiply this thing with, okay, let me write the whole thing. R equals to R DRU into e to the power minus 1 minus C lambda T into what? Into any one of these n spares should be working. So this 1 minus of 1 minus RT to the power n. Is this okay? This equation? Where I know that the active module has a constant failure rate lambda. And because I am using RT here, I also know if all the spares also have the same failure rate lambda, I can appropriately replace RT with e to the power minus lambda t. Are you there with me? Is this fine?
That e to the power term, is it like a probability distribution function?
E to the power minus lambda t, remember we said that when we did in the first class that when I have a constant failure rate lambda, then
Yes.
the reliability is given by e to the power minus lambda t.
Yes, sir. Yes, sir.
Right? Yes. So from that, we are saying that e to the power minus lambda t is fine. But when C becomes the probability that the fault will be correctly detected, then 1 minus C into lambda becomes the effective failure rate. And therefore, you will get that. You will multiply by RDRU and then you will add any one of the spares. Okay. I'm proceeding if there are no more questions here.
Sir, this is the first term of R dynamic, right? We need to add R active as well for the whole expression.
R active is no more required because you see R active, that is why I am saying what is e to the power minus, what is this one, this part? E to the power minus 1 minus C lambda t. What is this? This
Okay,
is
this is
the
the reliability for the module.
right,
Okay, so
of
yes.
the active, because the effective reliability of the active module is 1 minus C lambda. That is the effective failure rate of the active.
Yes, sir.
Given that C is the coverage factor.
Yes, sir. I got it.
Fault. Yes.
Thank you, sir. Yeah.
Okay. So as we told, we were looking at schemes where we want to reduce cost of an n modular system, and we were looking at to the case when spares can be dynamically added. So again, hybrid system is another one where an NMR masks. Fine, NMR. We talked about the problem of NMR. What was the problem of NMR? It is very nice at masking permanent and intermittent failures, but when reliability of a single module drops below a certain level, then NMR does not help. We saw that, and the total reliability of the system becomes very poor. For example, when a particular component is running for a very long time without replacement, and because of wear and tear, its reliability has reduced. So hybrid redundancy overcomes this by adding spare modules to replace active modules once they become faulty. And this is what we were saying. So a hybrid module consists of a core of n processors and m spares. So now instead of an active, we have a hybrid system. It's not only dynamic that we have only one active and the other spares. We have n processors. We have n processors like in an n modular system along with m spares. So now what happens? The output of the primaries are compared with voter to identify a faulty primary. In case of a fault, reconfiguration unit replaces faulty primary with a spare. Right? Okay. So what happens that in any case, you have these n primaries, the output of these n primaries here, the output of these n primaries go to the reconfiguration unit. then it is voted. The voted output comes the voted output comes out. That is fine. Up to this is an M of n system. This is fine, no issues. Now the output also goes to a comparison unit. This comparison unit, the output of each of the primaries is then compared with the output of the voter to find out which of the primaries are not working correctly. Okay, so see, the output of the voter is always the correct output because it's the majority output. And then here in these lines here, what are they saying? They are being, so the output of each of the n primaries are being compared with the output of the voter to find out which of the primaries are working correctly and which are not working correctly. So this was one of the problems with NMR. NMR could detect faults, but there was no mechanism to find out the faulty component and then replace it. We had this in dynamic. We did not explicitly say how. Now in this we are saying how is that is being done. So after that it will find out the primary, it will remove the faulty primary and replace it with a spare. Right? This is the system. The reliability of a hybrid system with a TMR core and M spares. So TMR core means triple modular redundancy and M spares. So what is the total number of components? Small m equals to m plus 3 is the total number of components. If small m equals to m plus 3 is the total number of components, then we are saying that reliability of this hybrid system is R voter into R reconfiguration unit into 1 minus m RT into this. So what does this mean? What does this mean? Any idea? Any idea what is it trying to say? This R hybrid equation, if I give you back the, we'll discuss this obviously. If I go back to the figure, or let us say this one. Okay, let us go back one slide and first see you have this reconfiguration unit. So you have a reconfiguration in this you have a reliability of this reconfiguration unit, this whole thing, this reconfiguration unit, and you also have a reliability of the voter. These two are fine and will be in series. That is also fine. Now what is the rest of the system? What is the rest of that equation telling? So R voter into R reconfiguration unit, that is fine, into what is it saying? What is it saying? In a triple modular redundant system with how many M spares? With M spares, if you have in a triple modular redundant system, any idea? Any idea? Any idea? Just look at this equation once and try to find out. Okay, in a triple modular redundant system, what are the cases in which the system will be able to correctly produce outputs? In which cases? In which cases? In a triple modular redundant system, simple triple modular redundant system, what will be the cases in which fault cases? What will be the fault cases in which the system will be able to produce correct outputs? Any idea? When all three components are working correctly or two of the components are working correctly? Right? So now we are saying that we have 3 plus m. We have 3 plus m modules. If we have 3 plus m modules, m into RT into 1 minus RT. What is this saying? What is this telling me? And what is this telling me? Now this part somebody has to tell me. What is m into RT into 1 minus RT to the power m minus 1? Tell me. What is this? Hello? Are you there with me?
All the
What is m into RT into 1 minus RT to the power m minus 1? What does this tell me?
the modules failing together.
One but all modules. Means
Yes, sir. Yes, sir.
one module will fail. Any one of the m modules, any one of the m modules will fail. The probability that any one of the m modules will fail, right? It is the probability that any one of the m modules will fail. And 1 minus RT to the power m is the probability that all m modules will fail. Sorry, all m modules will be working correctly. So 1 minus of m into RT, this whole thing, this whole thing now. What is this one telling me? This is the probability that either one, the probability that that the system for the probability for the cases that at most one module is failing. Either all modules are working correctly or one but all modules are working correctly. Is that okay?
Sir, 1 minus RT raised to m, that is all the m modules failing together, right?
Yes.
And 1 minus RT
1
raised to m
minus
minus
RT to the
1.
power n. Is it 1
Yeah.
minus RT to the yes, 1 minus RT to the power n. Yes.
And 1 minus RT raised to m minus 1, that is one module is working, but m
RT
minus 1 are
into.
failing. M minus 1 modules are failing. Right, exactly m minus 1 are failing.
Yes.
So the
Exactly, m
difference,
minus 1 are failing.
so the difference will give me exactly one module is working correctly, right?
Yes, m into RT, one module is working correctly and m minus 1 are not working correctly. That is m into RT into, right, in m into RT into 1 minus RT to the power m minus 1. That is one module is working correctly and m minus 1 are not working correctly. And 1 minus RT to the power m is telling me that all modules are not working correctly. Sorry, I told the opposite, na? Sorry. So 1 minus of m into RT into 1 minus RT to the power m minus 1 minus this one is telling me the rest. That means at least two of the modules are working correctly. Is that okay? Based on what you said, you corrected me. I was telling I was making a mistake.
Yes, sir. I
Right?
mean, I'm still not clear about that m times RT that you are multiplying there with 1
Right,
minus
right.
RT.
So, oh, no. So this one, this m times is telling me it is NC1. Sorry, MC1.
Okay,
You have
okay,
m
okay,
modules.
got it.
So the
Right,
point is that you have m, total is m modules. This small m modules. So small m is
correct,
m plus 3.
correct.
Small m is m plus 3 because you have three of them here, the primary 3, and capital M spares. So for this case, how many ways in which, so you can, if you are given this reconfiguration unit and the voter and you multiply the reliabilities of them, then this whole thing can be looked at small m components, where small m equals to m plus 3, right? This whole rest can be
Yes,
looked
sir.
at small m components, where small m equals to capital M plus 3. Now in that you are discarding the cases which 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 will lead to uh, a system crash. What are the cases which will lead to a system crash? All m modules are failing and m minus 1 modules are failing. So these two cases, the different ways in which these two cases can happen, if you can discard them out, then for the remaining cases, the only thing is that the voter will vote correctly and the reconfiguration unit will be able to correctly diagnose the primary, the error in the primary and replace it with a spare. So those reliabilities when multiplied, the work is 1 minus of this whole thing.
Yes, sir. Yes, got it.
But then somebody else also has to tell me yes. Somebody else has to ask a question. I am hearing your voice and Vinay's voice, and there was one other person who asked me something. But what about the others? Are they not understanding anything? Is it difficult? Do you want me to explain again? Especially because I made a small mistake while explaining this initially. So if you want me, I can explain this again. Hello, somebody else.
It is fine, sir. I thought of m plus 3 and I got confused.
Right. Okay. So assuming that any fault in the voter or comparison or reconfiguration unit will cause a system fault. In practice, okay. So now what these 2 points are trying to tell here is that what these 2 points are trying to tell here is that, see, the whole system is very again becomes very dependent on the voter and reconfiguration unit, and it is trying to say that in general not all faults are very important. So if the voter or and this reconfiguration unit works more or less correctly, then the system should work fine. Such a system in practice works fine. This is what they're trying to say. Okay. Then we come to duplex systems. So in a duplex system, so in a triplex system, in a triple modular redundant system, you can call it a triplex system. In a triplex system, you have 3 components doing the same task. In a duplex system, you have 2 components doing the same task. If the outputs are in agreement, then the result is assumed to be correct. If the outputs are different, we cannot identify the failed processor or you can say failed component. Then a higher level software has to decide how failure is to be handled. High level software or a high level function, whatever you want to say, a functionality has to have that. So this can be done using one of several methods. How? Then we come to something called acceptance tests. So acceptance test, as I told you that C was doing that acceptance test. You saw that coverage factor, that C probability that was coming. That was the probability that that a fault will be correctly detected through acceptance test. So acceptance test, it's a range check of each processor's output. Example, the pressure of a boiler must be within some known range. If it is outside that known range, then there is some problem with the boiler. We use semantic information of the task to predict which values of output indicate an error. What do we mean by semantic information? Knowledge of the system. Semantic information means in the context in which we are applying our method. In that context, some output ranges, for example, could be valid. Some of them are acceptable, some of them are not acceptable. So depending on that, you can predict which output is correct and which output is wrong. What is the scenario again? We are talking in terms of a duplex system. In a duplex system, as I said, you have two components doing the same thing. There is a comparator which compares the output. If the outputs match, then it is fine. If the outputs do not match, then one of the components may be in error, or both components may be in error. Then we do not have any mechanism like the triple modular redundancy to find which is the error. So we need a higher level system to detect an error, to detect which of the outputs is in error. So what you essentially do, each hardware component is subjected to some test vectors. So the whatever was the original function that the system was doing, that is stopped because the comparators did not match. Now our next objective becomes to find out which of these components were in error. So then each of these components will go through a separate test phase. All these, why are we doing? To reduce cost, because triple modular redundant system always solves our problem, but we have to have another additional system which could be costly. So as we are saying, we are looking at schemes as to by which the cost of the overall n modular system could be reduced. We looked at dynamic or hybrid systems. We looked at and now we are looking at duplex systems. So in this case, each of these components will be subjected to an acceptance test. So it will be given known inputs, and we will check for what the output is produced for these known inputs. If it is within a certain range, then we predict that there is an error. How should the acceptance range be picked? That is a big question. What is the acceptance range of a given output? So there are two things here. One is sensitivity, the probability that the test will recognize an erroneous output as such, and specificity, the probability that the test will identify a correct output as such. So what is sensitivity? The sensitivity is the probability that the the acceptance test will correctly pick a will correctly recognize an error. Sensitivity is the probability that the acceptance test will correctly recognize an error. And when will that happen? If the acceptance range of outputs is small. Because if the range of outputs is small, then whenever that the output is outside this range, I will say that there is an error. So the probability that the output will correctly recognize an error will become high. However, when the range is small, specificity reduces. What is specificity? The probability that the acceptance test will identify a correct output as such. What is this? So specificity tells me what is the probability that the acceptance test will be able to produce, will be able to correctly identify a correct output. So if the range is too small, if the range is small, then sometimes it will be able to find errors, that is fine. But there will be also a high probability that correct outputs will be stated to be wrong, will be deemed wrong. Correct outputs will be deemed wrong if the range is small. So then if the range is small, then specificity suffers, but sensitivity becomes high. On the other hand, if the range is wide, then sensitivity suffers, but specificity becomes high. So the range of outputs for which I will say that my component is giving correct output has to be very carefully chosen. This is what this whole thing tells us. and nothing more. So then what then comes, what are the different, we will finish off with duplex systems, then we will go to Byzantine failures, and then in the next class we will go into embedded communication network analysis from tomorrow. So, and there we will all obviously be using all the concepts that we have learned till now. So hardware testing. Both processors, you can think of them as components, are subjected to some test. The processor which fails the test is identified as faulty. Fine, again, the real life tests are never perfect, so there is a test coverage with respect to sensitivity and specificity. There is nothing much more in this. Okay, this part, let us go into this part, and then we will move to this, to Byzantine failures. Okay. So what is the reliability of a duplex system? So reliability of a duplex system is given by the reliability of the comparator into reliability of into this. What is this? The probability that both processors or both modules are working correctly, and the probability that one of the modules are working incorrectly, but that C in this tells me that probability that a faulty processor will be correctly diagnosed, identified, and disconnected. Any questions here with respect to R duplexity? Then we will be moving to Byzantine failures. Okay, somebody explain me this. Other than Vinay and this, whoever voices I have heard, I want somebody else to explain this equation to me. I have explained a lot. Now you explain me one. Yes, hello. Hello.
So the reliability of this system, this duplex system, is the reliability of this comparator, and then it is multiplied by this reliability of both the processor working correctly and or one of the processor working correctly, one is faulty. With the coverage
So,
factor C also, that it is being identified correctly that it is faulty.
no, explain the second part a bit more.
So
Explain
this
this part a bit more.
2CRT.
This part.
So
Yes.
this 2CRT part.
Yes, yes.
Sir, it is saying that one of the processor is faulty, and it is multiplied with C, that determines that the faulty
Why
processor
two?
is identified correctly.
Why two? Why two?
So 2C1, because there are two processors. This is a duplex system.
Either processor 1 is failing or processor 2 is
Yeah.
failing.
Yes, sir.
Yes, fine. So again, this is the last slide here. I think, yes, this is the last slide here in this part of the this hardware reliability testing part. So triplex duplex system is the triplex of a duplex system, nothing more. So in this approach ties together processors to form duplexes. A triplex is then formed out of these duplexes. When the processors in a duplex disagree, both of them are switched out of the system. The triplex duplex arrangement allows a simpler identification of faulty processors. Further, the triplex can continue to function even if only one duplex is left functional, since the duplex arrangement allows us to detect faults. This is nothing. Again, you have studied triplex, you have studied duplex. So triplex duplex system is a triplex over a duplex system, is a triple modular redundancy of 3 duplex systems. So you take the duplex system with the comparator, make 3 copies of it. The outputs of the comparator of 3 outputs of the 3 comparators goes to a voter, and you have a triplex duplex system. If I may ask, means why am I telling these structures? Because I have told you all this initially, all these things I have told you elaborately. Now you have to just maybe I may give you simple sums on reliability, simple questions relating to the reliability of the effective system. When you know what is the reliability of the duplex system, what is the reliability of a triplex system, you may need to in the exam to combine things. So you know the reliability of a triplex system, you know the reliability of a duplex system. What will happen to the effective reliability when you have a triplex of duplex system? Nothing very difficult, but you may need to practice a bit at home. Okay. Let us go to something different now. Till now, so we have mostly seen, till now we have mostly seen permanent failures, in which we are saying that either when a system fails, it crashes. We are saying that when a system fails, it produces no output, or it produces consistent incorrect outputs to everybody. But so the first one is called a fail stop system. I think I have told anywhere. No, the first one is called a fail stop system, and the second one, so what is a fail stop system? When the system crashes or fails, no output is produced, it has crashed. Like suppose a bulb is glowing fine. When there is a when it crashes, when it burns out, there is no light. So we have that picture in our mind, and we tend to think that all failures will be of that type, that it is working and then when it fails, there is no output produced. Or another simplistic case is that when it fails, it produces wrong outputs, but all wrong outputs are same and to everybody. Wherever this output is produced by this failed system, it produces the same wrong output. However, that may not always be the case. A very typical, practical, and hard to decipher error is the third type, where a failed component produces different incorrect outputs or correct outputs to different units. Suppose you have a sensor. That sensor is producing sensed outputs, means our output of the sensor goes to say 3 systems or 2 systems. Output of this sensor goes to 2 systems. So you have a sensor S, you have a sensor S, and it goes to 2 systems. Let us say R1 and R2. And it says that R1 that the output is 1, and it says output R2 that the output is 2. So the sensor is in error, fine, but it tells 2 different outputs to the 2 systems, to the 2 controllers. Let us say the sensor, the output from the sensor goes to the controller. R1 is a controller, R2 is another controller, and it receives 2 different sensor inputs. Now, how can they possibly try to, so these types of failures are called Byzantine failures. So no consistency is guaranteed. Different users may see different values of the output. So R1 is seeing a different value of the output than R2. Now, how could you possibly find out a possible error here? Maybe that R1 and R2 can exchange messages to understand what was passed to them. Say say R2 gets from R1, what did you receive from S? Say R1 if it says 1. And then R1 also asks, what did you receive from S? Then R2, let us say it says 2. So then R1 and R2 both know that there is some problem. But will they be able to find out that the sensor was in error, was erroneous, was faulty? Yes or no? Yes, somebody?
There needs to be a comparator node that compares the both R1 and R2 feeds.
No, see the situation that I told you. S has produced R1 and R2 are two controllers. R1 receives and both read the same sensor. When reading the sensor has produced output 1 to R1 and has produced output 2 to R2. Now, to check whether the sensor is working correctly, so R1 decides to also know from R2 what is the because suppose R1 knows that R2 will take the same sensor output. So it exchanges message a message to know from R2 what is the output it got from S. So then R1 sees two outputs. So gets two inputs. From S it gets 1, from R2 it gets 2. Now you are saying, let us say the comparator is there. Then
Then it is possible to detect the difference. Like it
no,
is
it's
not
not
from two.
possible. Why? Yeah, it is not possible. It is not possible because the error could be in R2 as well. You do not know whether the sensor gave me a wrong input or there is a problem with R2, right? So this problem is called the Byzantine generals problem. This is the simplest form of the Byzantine generals problem. Okay, let us get into and look into this. So Byzantine failure, no consistency is guaranteed. Different users may see different values of the output. A computer system, as I told you, uses sensor inputs to control some process. Is there a way to ensure that the output of a sensor is seen consistently by all the functional processors despite the sensor exhibiting Byzantine failure? So this problem was originally uncovered at NASA and studied right back from 1978, and from 1999 onwards, multiple algorithms have come up, mostly uh, for the blockchain technology, because this forms one of the basis of the blockchain technology. Okay. So now, with that understanding of the basic problem that we encountered, we will go into the Byzantine generals problem. So the Byzantine army is besieging a city, each division commanded by its own general. The commander-in-chief coordinates the division. So there is a Byzantine army. That army is trying to attack a city. It's trying to take over a city. And how does it take over the city? It tries to, the army divides itself into multiple groups and tries to attack from all sides. Now the problem is that there are many trenches, cannons in between, and each of the army subunits cannot see each other. The only way by which they can communicate is by using a messenger. So the messenger takes the messengers. The messengers are two things. There is a commander in chief and there are commanders for each army subunits. The commander in chief gives orders to each of these sub commanders, and the sub commanders can communicate among themselves through messengers. The problem is this, that it is it is fine. They see, the city also has its own defenses. If all the generals, if all the lieutenant commanders, there is a main commander, commander in chief, and there are lieutenant commanders. If all the lieutenant commanders decide and say attack together, then they will win over the city. But if some of them attack, then they will lose. Some of them attack and some of them do not attack, then they will lose. So the problem is that what happens when some of these commanders are traitors? For the time being, we will see that we will assume that the messengers are not traitors. So again, if I tell you the problem, you have some Byzantine army, some army called Byzantine army. That army is trying to besiege a city. They're trying to take over a city. And the army has several divisions, each division headed by a lieutenant. And overall army is commanded by a commander-in-chief. This commander-in-chief is our censor. And each of these division heads are our R1, R2 that we told. Each lieutenants. These lieutenants are R1, R2s, etc. Now we are saying that this main sensor could be faulty, and each of these components R1, R2, etc. could be faulty. So the faulty here is equivalent to this traitor. The sensor, the commander-in-chief is a traitor, meaning that it gives different outputs to different our different army lieutenants. Now the 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 commander-in-chief or the controller has just two alternatives, either to attack or retreat. But the problem, as I told you, if all divisions do not concur in the decision that attack, then they will lose. So what has to happen is that either they all retreat together, then everybody is saved, or they all attack together. Otherwise, there will be a huge loss to the army. If the actions taken by each division is not consistent with that of others, the army will be defeated. The commands are sent in the form of two-party oral messages. So two-party oral messages meaning that you have a horse-ridden messenger which takes the message from one of the lieutenants and gives the message to another lieutenant. So this is the only two-party oral messages that you have. And for the time being, we are assuming that the messages are not lost. Now, there are two criterions for success. So when do I say, what do I want to achieve? Okay, firstly, what do I want to achieve? In the presence of traitors, I want to achieve the following. In the presence of traitors, I want to achieve the following: that all loyal generals, so IC1 I am talking, all loyal generals must agree on the same plan of actions. There will be traitors, so you cannot do anything with the traitors, but whoever are the loyal generals or loyal lieutenants, they must agree on the same plan of action, right? If the commander-in-chief is loyal, if the commander-in-chief is not a traitor, then the loyal generals or the loyal lieutenants must obey his order. Okay, so the first case is that the commander-in-chief could be a traitor, but even if if he is a traitor, he is not giving the same output to everybody. So even in the presence of that, you need a mechanism in which all the loyal generals or the loyal lieutenants, what do we mean by loyal lieutenants in our parlance? Correctly functioning controllers or correctly functioning units. All the correctly functioning units should agree on the same plan, which should agree on the same output. should agree that we have to do this. Whatever, we don't know what our general, our commander-in-chief has told us, but we are all loyal. We are all functioning correctly. So we should have, we should go ahead understanding that this is the this is the action we have to take. And the second is that if the commander-in-chief is loyal, that means if the commander-in-chief is working, the sensor is functioning correctly, then the loyal generals or the loyal lieutenants must take the order, must obey the order that he has actually passed. So it is not sufficient that if the commander-in-chief is loyal, or if the sensor is working correctly, it is not sufficient that the correctly functioning controllers decide on the same output. It is not sufficient. They will have to decide on the same output, same plan of action, but that plan of action has to be the one that has been given by the commander-in-chief. And the aim of the algorithm is not to identify the traitors. Have I been able to explain the problem? I am expecting questions on this. Can somebody explain to me what he has understood? Yes? Hello?
So we can portray this problem as the sensor and controller problem only. So there are two cases. The first thing is that all the controllers are working perfectly fine. So in that case, whatever value this sensor passes, they'll take that value and the final output will be same for all the cases. And in the other case, if there is a fault in controller, so that fault should be such that even the wrong output should come out to be same.
If the fault is in the sensor.
Yeah, sorry. Yeah.
If the fault is in the sensor, then the correctly functioning, even if the sensor is faulty, and if you have a large number of controllers taking that sensor input, not all of these controllers need to be correct. There could be the sensor is wrong and some of the controllers could also be wrong, but whoever is working correctly should form a quorum and decide that this is what we should do. Functioning of all the correctly functioning controllers. On the other hand, if the sensor is working correctly and some of the controllers are not working correctly, then the correctly functioning controller should decide on the same plan of action, and that plan of action should be the one passed by the sensor. I think this is okay, right?
Yes, sir.
Yes, fine. Okay. So the traitors aim, one or more of the generals, including commander-in-chief, could be a traitor. The aim of the traitors is to cause the Byzantine army to be defeated by violating the conditions of victory. Why? Because they have been bribed by the city. Okay. So as we told of the initial problem, let us say we have a commander-in-chief and two divisional generals A and B. So sensor and two outputs R1 and R2. If the commander-in-chief is a traitor, it tells A to attack and B to retreat. Case 2, if the commander-in-chief is loyal but A is a traitor, it tells both A and B to attack. However, A tells B that his orders from the commander-in-chief are to retreat. What should B do? Nothing. The problem cannot be solved for a 3-node system with one Byzantine failure. So, in general, the problem is solvable. When is the problem solvable? We will not go into the proof right now. The problem is solvable if you have 3m, if m are faulty nodes, if there are m faulty nodes, then if you have 3m plus 1 total number of, in a 3m plus 1 node system, if you have m faulty nodes, then you can work correctly. So you have n nodes, where n nodes, in that case, if you have one sensor and two controllers R1, R2, then this is a 3-node system. So one of them is the sensor and the other two are the controllers. In an n-node system, you have one controller and one sensor and n-1 controllers. Now, in general, we are saying that a system is solvable. For example, if you have one, we saw that if you have two controllers and one sensor, one failure cannot be tolerated. You cannot tolerate. When can that be tolerated? When you have 3m plus 1, 3 into 1 plus 1. So if you had a 4-node system, then you can solve the problem. We'll see how. So what we are trying to say is that we have one sensor and that passes the outputs to 3 controllers. If you have such a system, then you have a 4-node system. So n equals to 4, 1 plus 3. So in that case, your problem is solvable. Okay. The general approach. So then let us see how the algorithm works. The commander-in-chief sends his order to each of the divisional generals. Each divisional general recursively uses the Byzantine general's algorithm to disseminate to his colleagues the order he received from the commander-in-chief. So the key algorithm parameter is m, the maximum number of traitors to be allowed for. So as we told, we need 3m plus 1 total number of nodes, where m is the number of failed nodes. And what is the algorithm approach? The algorithm approach is this. Instead of going into the algorithm, it is not written nicely, I think, but I'm telling you. So let us say B is the algorithm, where n is the total number of inputs and m is the total number of failures. So if this one, so the commander-in-chief passes messages to all the controllers. Now each controller then calls n-1, m-1. So what does this mean? So for Bn, m, the commander-in-chief passes the message to all of the n-1 controllers. So the commander-in-chief is the source. It passes the message to all n-1 other controllers. Then each controller acts as the source. See, in the previous one, I told that this algorithm is called recursively. Then each controller acts as the source and passes the message to the remaining n-2 controllers. So whom does it not send to? From whom it has already received. So it passes to the n-2 remaining ones, and this goes on until m becomes 0. So then this message, this Bn-1, m-1, will be received by the different controllers. Then they will again recursively call B of n-2, m-2, and this will go on continuing until m becomes 0. And what does n-2 means? N-2 means this message will be passed. Hello, 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 hello. Am I audible? Hello.
Yes, sir.
Yes,
Yes,
yes. It actually, my connection went off. That is why. So what does Bn-2, m-2 mean? Bn-2, m-2 means that you will send this message to the remaining n-3 controllers, which two will you not send to? The original commander-in-chief and the controller from which you received B n-1 m-1. Okay. So likewise then it will call this one will be received by the controllers and it will call B n-3 m-3. Right? So what is it telling? The commander-in-chief sends his order to each divisional general. Each divisional general obeys the order he receives from the commander-in-chief. Okay. Then the commander-in-chief sends his order to each divisional general. Then in step 2, what do you do? So this OM, this M is basically what I just told you. See now, after I have explained this in the previous slide, try to read these 3 steps. What are these 3 steps saying? The commander-in-chief sends his order to each divisional general. Each divisional general then uses you read this as B of n comma m. And then you read this as B of n-1 comma m-1. Because the n-1 is already there, so because n is already there, n-1 helps you to understand to whom will you pass and whom not to. That's it. Each divisional general uses B n-1 m-1 to disseminate the order he got from commander-in-chief. Right? At the end of this step, each divisional general has a vector containing the order he received from the commander-in-chief and the order disseminated by every other divisional general. Suppose I am controller divisional general number 1. So after at the end of step 2, what do I have? I have received, I am say R1 and I have 3 other R's, R2 and R3. At the end of step 2, what do I have? I have a message that I received from the sensor s.r1, s to sensor, right? Then what have I got? I have also got one from s dot r2 to r1, means r1 gets what? So if you remove that r1, so it has got 3 messages. One is s, the other is s dot r2, the other is s dot r3. Are you with me at the end of step 2? So it has got one message. So this is the command, S is the commander in chief, R2 and R3 are the 2 other controllers. I am at R1, I am at R1. So I have this vector of 3 outputs. One is the original output that I got from the commander in chief or the sensor. The other is the output that I received from R2 and R3, because each Bn minus 1 m minus 1, what it has done, each divisional general uses Bn minus 1 m minus 1 to disseminate the order got from the commander in chief. So what has R2 got from commander in chief? S dot R2. S. So R2 got from S. So S dot R2 he then passes to R1. Similarly, R3 receives something from S, that he whatever he gets from R3, it passes it to R1. So R1 now has a vector of 3 messages. One is the original S, the second is S dot R2, the third is S dot R3. Okay. In step 3, each divisional general follows the majority decision from the vector obtained in step 2. So now this step here, before coming to this step, we need to understand that step 2 is a recursive step. It will go on doing until m equals to 0. I'll take an example. if the total number of if this is what we told you, if the total number of generals is n greater than equals to m 3m plus 1, then running OMM will ensure that the interactive consistency conditions. What is interactive consistency conditions? These two conditions. This, all loyal generals must agree on the same plan of action, and if the commander-in-chief is loyal, the loyal generals must obey his order. So these two conditions will be satisfied, as I told you. And however, if n is less than 3m plus 1, then no algorithm exists that can ensure interactive conditions for all cases. Now, this example again is a bit long. Maybe we will take it tomorrow. I will quickly explain this again in 5-10 minutes, and then we will go into the example and understand this for at least 2-3 cases, how this is obtained. I do not want to continue today anymore, and because the example is a bit long, and if I start, I won't be able to complete. Tomorrow, 5 o'clock, we will do it. Huh. But if you have questions on the algorithm, if you have not understood the algorithm, you please ask me today, so that tomorrow we should be we should be just going ahead towards the example. Do you have any confusion in how the algorithm works? If you ask me a question, I should be able to answer you.
Sir, where can I find this topic in a book? In which
I
book?
have given you the yes, I have given you the book, right? If you see the first slide, in the last 2 classes also, I have told you that the major reference is fault tolerant systems by Israel Koren and C. Mani Krishna. So the first part of this course, this hardware fault tolerance, reliability, and the reliability analysis of embedded control networks, these two I will be teaching from this book. But then you go into the book, fine. You and the other point is that you should get a soft copy of this book somewhere in the net for free. If you search a bit, you will get this book in the net.
Yes, sir.
Now, any problem with algorithm? Any problem with the idea of Byzantine failures? How is it different from a general failure? Okay. If there is nothing, then I will stop here today. I want to start the example with a fresh mind tomorrow. Yes? Is that fine?
Okay, sir, it's fine, sir.
Yes.